Light. The light we see is the part of the electromagnetic radiation, that is the visible light spectrum, which is that which can be perceived by the human eye. Scientists say that visible light usually has wavelengths in the range of 400 to 700 nanometers, corresponding to frequencies of 750 to 420 terahertz, between infrared and ultraviolet. In physics, the term light may refer more broadly to the electromagnetic radiation of any wavelength, whether visible or not. In this sense, gamma rays, X-rays, microwaves and radio waves are also light. The primary properties of light are intensity, propagation direction, frequency, wavelength, spectrum and polarization. Like all types of electromagnetic radiation, visible light propagates by massless elementary particles called photons that represent the quanta of an electromagnetic field, and can be analyzed as both waves and particles. Our star, Sol, which we commonly know as the Sun, is our main source for light and heat on planet Earth. Generally, electromagnetic radiation is classified by wavelength into radio waves, microwaves, infrared, the visible spectrum that we perceive as light, ultraviolet, X-rays and gamma rays. The designation radiation excludes static electricity, magnetic and near fields. The behavior of electromagnetic radiation depends on its wavelength. Higher frequencies have shorter wavelengths and lower frequencies have longer wavelengths. When electromagnetic radiation interacts with single atoms and molecules, its behavior depends on the amount of energy per quantum that it carries. Electromagnetic radiation in the visible light spectrum consists of quanta or photons at the lower end of the energies. Photons are capable of causing electronic excitation within molecules, which leads to changes in the bonding or chemistry of the molecule. At the lower end of the visible light spectrum, electromagnetic radiation becomes invisible to humans at the infrared band. Infrared photons no longer have enough individual energy to cause a lasting molecular change in the visual molecule, retinal in the human retina, which when changed, triggers the sensation of vision. There are animals that are sensitive to various types of infrared, but not by means of quantum absorption. It depends on a kind of natural thermal imaging, in which tiny packets of cellular water are raised in temperature by the infrared radiation. Above the range of visible light, ultraviolet light becomes invisible to humans, mostly because it is absorbed by the cornea below 360 nanometers, and the internal lens below 400 nanometers. The rods and cones located in the retina of the human eye cannot detect the very short ultraviolet wavelengths and are damaged by ultraviolet. Animals with eyes that do not require lenses such as insects and shrimp are able to detect ultraviolet, by quantum photon absorption mechanisms, in much the same chemical way that humans detect visible light. Various sources define visible light as narrowly as 420 to 680 nanometers to as broadly as 380 to 800 nanometers. Under ideal laboratory conditions, people can see infrared up to at least 1050 nanometers. Children and young adults may perceive ultraviolet wavelengths down to about 310 to 313 nanometers. Plant growth is also affected by the color spectrum of light, a process known as photomorphogenesis. The speed of light in the physical universe in a vacuum has been determined to be 299,792,458 meters per second, or 186,282 miles per second. All forms of electromagnetic radiation appear to move at exactly this same speed in a vacuum. If we take the double slit and quantum entanglement experiments and emergence theory into account, is it possible that the speed of light only applies for this reality? Wouldn't there have to be a system or construct that allows the speed of light and light itself to exist? Galileo attempted to measure the speed of light in the 17th century. An early experiment to measure the speed of light was conducted by Ole Rømer, a Danish physicist, in 1676. Using a telescope, Rømer observed the motions of Jupiter and one of its moons, Io. Noting discrepancies in the apparent period of Io's orbit, he calculated that light takes about 22 minutes to traverse the diameter of Earth's orbit. If Rømer had known the diameter of the Earth's orbit, he would have calculated a speed of 227 million meters per second. Another more accurate measurement of the speed of light was performed in Europe by Hippolyte Fizeau in 1849. Fizeau directed a beam of light at a mirror several kilometers away. A rotating cog wheel was placed in the path of the light beam as it traveled from the source to the mirror and then returned to its origin. Fizeau found that at a certain rate of rotation, the beam would pass through one gap in the wheel on the way out and the next gap on the way back. Knowing the distance to the mirror, the number of teeth on the wheel and the rate of rotation, Fizeau was able to calculate the speed of light as 313 million meters per second. Léon Foucault carried out an experiment which used rotating mirrors to obtain a value of 298 million meters per second in 1862. Albert A. Michelson conducted experiments on the speed of light from 1877 until his death in 1931. He refined Foucault's methods in 1926 using improved rotating mirrors to measure the time it took light to make a round trip from Mount Wilson to Mount San Antonio in California. The precise measurements yielded a speed of 299,796,000 meters per second. The effective velocity of light in various transparent substances containing ordinary matter is less than in vacuum. For example, the speed of light in water is about 3/4 of that in a vacuum. Two independent teams of physicists were said to bring light to a complete standstill by passing it through a Bose-Einstein condensate of the element rubidium. The popular description of light being stopped in these experiments refers only to light being stored in the excited states of atoms, then re-emitted at an arbitrary later time, as stimulated by a second laser pulse. During the time it had stopped, it had ceased to be light. The study of light and the interaction of light and matter is termed optics, a surprisingly important research area in modern physics. The observation and study of optical phenomena such as rainbows and the aurora borealis offer many clues as to the nature of light. Refraction is the bending of light rays when passing through a surface between one transparent material and another, as described by Snell's law. When a beam of light crosses the boundary between a vacuum and another medium, or between two different media, the wavelength of the light changes, but the frequency remains constant. If the beam of light is not orthogonal to the boundary, the change in wavelength results in a change in the direction of the beam. The refractive quality of lenses is frequently used to manipulate light in order to change the apparent size of images. Magnifying glasses, spectacles, contact lenses, microscopes and refracting telescopes are all examples of this manipulation. A body at a given temperature emits a characteristic spectrum of black-body radiation. The radiation emitted by the chromosphere of the Sun at around 6000 degrees Kelvin, 5730 degrees Celsius or 10,340 degrees Fahrenheit. It peaks in the visible region of the electromagnetic spectrum when plotted in wavelength units. Roughly 44% of sunlight energy that reaches the ground is visible. A common thermal light source in history are the glowing solid particles in flames, but these also emit most of their radiation in the infrared, and only a fraction in the visible spectrum. The peak of the black-body spectrum is in the deep infrared, at about the 10 micrometer wavelength, for relatively cool objects like human beings. As the temperature increases, the peak shifts to shorter wavelengths, producing first a red glow, then a white glow and finally a blue-white color as the peak moves out of the visible part of the spectrum, and into the ultraviolet. These colors can be seen when metal is heated to red-hot or white-hot. Blue-white thermal emission is not often seen, except in stars. A commonly seen pure blue color in a gas flame or a welder's torch is because of molecular emission, notably by 425 nanometer wavelength hydrocarbon radicals, and is not seen in stars or pure thermal radiation. Atoms emit and absorb light at characteristic energies. This produces emission lines in the spectrum of each atom. Emission can be spontaneous, as in light-emitting diodes, gas discharge lamps, neon signs or mercury vapor lamps. Emission can also be stimulated, as in a laser or a microwave maser. Deceleration of a free charged particle, such as an electron, can produce visible radiation. Particles moving through a medium faster than the speed of light in a medium can produce visible Cherenkov radiation, cyclotron radiation, synchrotron radiation and Bremsstrahlung radiation. Certain chemicals produce visible radiation by chemoluminescence. In living things, this process is called bioluminescence. For example, fireflies produce light by this means. Vampire squids use it to hide themselves from prey, and boats moving through water can disturb plankton, producing a glowing wake. Certain substances produce light when they are illuminated by more energetic radiation, a process known as fluorescence. Some substances emit light slowly after excitation by more energetic radiation. This is known as phosphorescence. Phosphorescent materials can also be excited by bombarding them with subatomic particles. Cathodoluminescence is one example. This mechanism is used in cathode ray tube, television sets and computer monitors. Light is measured with two main alternative sets of units. Radiometry consists of measurements of light power at all wavelengths, while photometry measures light with wavelength weighted with respect to a standardized model of human brightness perception. Photometry is useful, for example, to quantify illumination or lighting intended for human use. Photometry units are different from most systems of physical units in that they take into account how the human eye responds to light. The cone cells in the human eye are of three types which respond differently across the visible spectrum, and the cumulative response peaks at a wavelength of around 555 nanometers. Two sources of light which produce the same intensity in watts per meter squared of visible light do not necessarily appear equally bright. The photometry units are designed to take this into account and therefore are a better representation of how bright a light appears to be than raw intensity. They relate to raw power by a quantity called luminous efficacy and are used for purposes like determining how to best achieve sufficient illumination for various tasks in indoor and outdoor settings. The illumination measured by a photocell sensor does not necessarily correspond to what is perceived by the human eye. Photocells and charge-coupled devices tend to respond to some infrared, ultraviolet or both. Light exerts physical pressure on objects in its path, a phenomenon which can be deduced by Maxwell's equations, but can be more easily explained by the particle nature of light. Photons strike and transfer their momentum. Light pressure is equal to the power of the light beam divided by c, the speed of light. Due to the magnitude of the speed of light, the effective light pressure is negligible for everyday objects. For example, a 1 mW laser pointer exerts a force of about 3.3 piconewtons on the object being illuminated. Lifting a US penny would require about 30 billion 1 mW laser pointers. However, in nanometer scale applications, such as nano-electromechanical systems, the effective light pressure is more significant, and exploiting light pressure to drive nano-electromechanical mechanisms and to flip nanometer scale physical switches in integrated circuits is an active area of research. At larger scales, light pressure can cause asteroids to spin faster, acting on their irregular shapes as on the vanes of a windmill. The possibility of making solar sails that would accelerate spaceships in space is also under investigation. The motion of the Crookes radiometer was originally attributed to light pressure, but the characteristic Crookes rotation is the result of a partial vacuum. This should not be confused with the Nichols radiometer, in which the motion caused by torque is directly caused by light pressure. As a consequence of light pressure, Einstein in 1909 predicted the existence of radiation friction which would oppose the movement of matter. Usually light momentum is aligned with its direction of motion. However, for example, in evanescent waves momentum is transverse to the direction of propagation. In the 5th century BC, Empedocles postulated that everything was composed of 4 elements: fire, air, earth and water. He believed that Aphrodite made the human eye out of the 4 elements and that she lit the fire in the eye which shone out from the eye, making sight possible. If this were true, then one could see during the night just as well as during the day, so Empedocles postulated an interaction between rays from the eyes and rays from a source, such as the sun. In about 300 BC, Euclid wrote Optica, in which he studied the properties of light. Euclid postulated that light traveled in straight lines, describing the laws of reflection and studying them mathematically. He questioned that sight is the result of a beam from the eye, because he asked how one can see the stars immediately, if one closes one's eyes, then opens them at night. If the beam from the eye travels infinitely fast, this is not a problem. In 55 BC, Lucretius, a Roman who carried on the ideas of earlier Greek atomists, wrote in On the Nature of the Universe, that the light and heat of the sun are composed of minute atoms which, when shoved off, lose no time in shooting right across the interspace of air in the direction imparted by the shove. Despite being similar to later particle theories, Lucretius's views were not generally accepted. In the 2nd century, Ptolemy wrote about the refraction of light in his book, Optics. In ancient India, the Hindu schools of Samkhya and Vaishika, from around the early centuries AD, developed theories on light. According to the Samkhya school, light is one of the 5 fundamental subtle elements or tanmatra, out of which emerge the gross elements. The atomicity of these elements is not specifically mentioned, and it appears that they were actually taken to be continuous. On the other hand, the Vaishika school gives an atomic theory of the physical world on the non-atomic ground of ether, space and time. The basic atoms are those of earth, Prithvi, water, Pani, fire, Agni, and air, Vayu. Light rays are taken to be a stream of high velocity of terahertz or fire atoms. Particles of light can exhibit different characteristics depending on the speed and the arrangements of the terahertz atoms. The Vishnu Purana refers to sunlight as the 7 rays of the sun. The Indian Buddhists, such as Dignaga in the 5th century and Dharmakirti in the 7th century, developed a type of atomism that is a philosophy about reality being composed of atomic entities that are momentary flashes of light or energy. They viewed light as being an atomic entity equivalent to energy. René Descartes held that light was a mechanical property of the luminous body, rejecting the forms of Ibn al-Haytham and Whitlow as well as the species of Bacon, Grosseteste, and Kepler. In 1637 he published a theory of the refraction of light that assumed, incorrectly, that light traveled faster in a denser medium than in a less dense medium. Descartes arrived at this conclusion by analogy with the behavior of sound waves. Although Descartes was incorrect about the relative speeds, he was correct in assuming that light behaved like a wave and in concluding that refraction could be explained by the speed of light in different media. Descartes is not the first to use the mechanical analogies, but because he clearly asserts that light is only a mechanical property of the luminous body and the transmitting medium, Descartes' theory of light is regarded as the start of modern physical optics. Pierre Gassendi, an atomist, proposed a particle theory of light which was published in the 1660s. Isaac Newton stated in his Hypothesis of Light of 1675 that light was composed of corpuscles or particles of matter which were emitted in all directions from a source. One of Newton's arguments against the wave nature of light was that waves were known to bend around obstacles, while light traveled only in straight lines. He did, however, explain the phenomenon of the diffraction of light, which had been observed by Francesco Grimaldi, by allowing that a light particle could create a localized wave in the ether. Newton's theory could be used to predict the reflection of light, but could only explain refraction by incorrectly assuming that light accelerated upon entering a denser medium because the gravitational pull was greater. Newton published the final version of his theory in his Optics of 1704. His reputation helped the particle theory of light to hold sway during the 18th century. The particle theory of light led Laplace to argue that a body could be so massive that light could not escape from it. In other words, it would become what is now called a black hole. Laplace withdrew his suggestion later, after a wave theory of light became firmly established as the model for light. The fact that light could be polarized was for the first time qualitatively explained by Newton using the particle theory. Etienne Louis Malus in 1810 created a mathematical particle theory of polarization. Jean-Baptiste Biot in 1812 showed that this theory explained all known phenomena of light polarization. At that time, polarization was considered as the proof of the particle theory. To explain the origin of colors, Robert Hooke developed a pulse theory and compared the spreading of light to that of waves in water in his 1665 work Micrographia Observation 9. In 1672 Hooke suggested that light's vibrations could be perpendicular to the direction of propagation. Christian Huygens worked out a mathematical wave theory of light in 1678, and published it in his treatise on light in 1690. He proposed that light was emitted in all directions as a series of waves in a medium called the luminiferous ether. As waves are not affected by gravity, it was assumed that they slowed down upon entering a denser medium. The wave theory predicted that light waves could interfere with each other like sound waves, as noted around 1800 by Thomas Young. Young showed by means of a diffraction experiment that light behaved as waves. He also proposed that different colors were caused by different wavelengths of light and explained color vision in terms of 3 colored receptors in the eye. Another supporter of the wave theory was Leonhard Euler. He argued in Nova Theoria Lucis et Colorum of 1746 that diffraction could more easily be explained by a wave theory. In 1816 André-Marie Ampère gave Augustin-Jean Fresnel an idea that the polarization of light can be explained by the wave theory if light were a transverse wave. Later, Fresnel independently worked out his own wave theory of light, and presented it to the Académie des Sciences in 1817. Siméon Denis Poisson added to Fresnel's mathematical work to produce a convincing argument in favor of the wave theory, helping to overturn Newton's corpuscular theory. By the year 1821, Fresnel was able to show via mathematical methods that polarization could be explained by the wave theory of light, only if light was entirely transverse, with no longitudinal vibration whatsoever. The weakness of the wave theory was that light waves, like sound waves, would need a medium for transmission. The existence of the hypothetical substance luminiferous ether proposed by Huygens in 1678 was cast into strong doubt in the late 19th century by the Michelson-Morley experiment. Newton's corpuscular theory implied that light would travel faster in a denser medium, while the wave theory of Huygens and others implied the opposite. At that time, the speed of light could not be measured accurately enough to decide which theory was correct. The first to make a sufficiently accurate measurement was Léon Foucault, in 1850. His results supported the wave theory and the classical particle theory was finally abandoned, only to partly re-emerge in the 20th century. In 1845, Michael Faraday discovered that the plane of polarization of linearly polarized light is rotated when the light rays travel along the magnetic field direction in the presence of a transparent dielectric, an effect now known as Faraday rotation. This was the first evidence that light was related to electromagnetism. In 1846 he speculated that light might be some form of disturbance propagating along magnetic field lines. Faraday proposed in 1847 that light was a high-frequency electromagnetic vibration, which could propagate even in the absence of a medium such as the ether. Faraday's work inspired James Clerk Maxwell to study electromagnetic radiation and light. Maxwell discovered that self-propagating electromagnetic waves would travel through space at a constant speed, which happened to be equal to the previously measured speed of light. From this, Maxwell concluded that light was a form of electromagnetic radiation. He first stated this result in 1862 in On Physical Lines of Force. In 1873, he published a treatise on electricity and magnetism, which contained a full mathematical description of the behavior of electric and magnetic fields, still known as Maxwell's equations. Soon after, Heinrich Hertz confirmed Maxwell's theory experimentally by generating and detecting radio waves in the laboratory and demonstrating that these waves behaved exactly like visible light, exhibiting properties such as reflection, refraction, diffraction and interference. Maxwell's theory and Hertz's experiments led directly to the development of modern radio, radar, television, electromagnetic imaging and wireless communications. In quantum theory, photons are seen as wave packets, as described in the classical theory of Maxwell. Quantum theory was needed to explain effects with visual light, that Maxwell's classical theory could not. In 1900 Max Planck, attempting to explain black-body radiation, suggested that although light was a wave, these waves could gain or lose energy only in finite amounts related to their frequency. Planck called these lumps of light energy quanta. In 1905, Albert Einstein used the idea of light quanta to explain the photoelectric effect and suggested that light quanta did exist. In 1923 Arthur Holly-Compton showed that the wavelength shift seen when low-intensity X-rays scattered from electrons. This Compton scattering could be explained by a particle theory of X-rays, but not a wave theory. In 1926 Gilbert N. Lewis named these light quanta particles photons. Eventually the modern theory of quantum mechanics came to picture light as both a particle and a wave. As in the case for radio waves and the X-rays involved in Compton scattering, physicists have noted that electromagnetic radiation tends to behave more like a classical wave at lower frequencies, but more like a classical particle at higher frequencies, but never completely loses all qualities of one or the other. visible light, which occupies a middle ground in frequency, can easily be shown in experiments to be describable using either a wave or particle model, or sometimes both. In February 2018, scientists reported, for the first time, the discovery of a new form of light, which may involve polaritons, could be useful in the development of quantum computers. Quantum entanglement is the phenomenon that occurs when a group of particles are generated, interact, or share spatial proximity in a way such that the quantum state of each particle of the group cannot be described independently of the state of the others, including when the particles are separated by a large distance. The topic of quantum entanglement is at the heart of the disparity between classical and quantum physics. Entanglement is a primary feature of quantum mechanics not present in classical mechanics. Measurements of physical properties such as position, momentum, spin, and polarization performed on entangled particles can, in some cases, be found to be perfectly correlated. According to the relational interpretation of quantum mechanics, first proposed by Carlo Rovelli, observations such as those in the double-slit experiment result specifically from the interaction between the observer, the measuring device, and the object being observed or physically interacted with, not any absolute property possessed by the object. In the case of an electron, if it is initially observed at a particular slit, then the observer particle, photon-electron, interaction includes information about the electron's position. This partially constrains the particle's eventual location at the screen. If it is observed or measured with a photon, not at a particular slit but rather at the screen, then there is no which path information as part of the interaction, so the electron's observed position on the screen is determined strictly by its probability function. In physics, the view of the universe and its workings as the ebb and flow of information was first observed by Wheeler. Many views of the multiverse emerged. The first one proposes that the universe is a quantum computer, while the other one proposes that the system performing the simulation is distinct from its simulation, or the universe. The system performing the simulation would possess the ability to move faster than the speed of light to be able to create the physical universe simulation. In metaphysics, light is the universe's way of transferring packets of intelligent energy into consciousness throughout spacetime. Those packets of intelligent light energy frequency are also called light symbol codes or DNA fire letters. Each DNA strand corresponds to a fire letter or fire code built upon electromagnetic impulses of sound arranged in patterned sequences. Each fire letter corresponds to a dimensional frequency band of consciousness, in the universal tree of life, or the 12-tree grid. The 12-tree grid is level 1 of the light body. It is the architecture of our multidimensional consciousness. Light bodies are vehicles that allow for existence in the higher planes of reality. Transcending the astral, causal, mental, and etheric planes to arrive and reside on the atmic plane and return at will. Collectively, all the fire letter code sequences correspond to the 12 DNA strand matrix, which is the original genetic construction code of the human species. These light codes are delivered to the planet and to a human body through energy frequency current, which is called Kundalini. Light is a manifestation pattern of electromagnetic energy created by a combination of multiple bands of frequency within a dimension of space-time. The various color spectrums of light delineate the dimensional quality of its energy frequency and its location within space-time. Nanolight particles and waves hold both properties of light and sound, which are the functioning base pairs of the same consciousness energy unit. When the quantum base pairs unite with the primal substance of God's source, this allows a feedback loop in our particle structure to circulate the eternal supply of God's source through our bodies and the planet. The audible life stream is the inner sound current, the word or light and sound of God. The Shabd is the essence of the Creator, which is available to all human beings. It can be heard by the inner ears, according to the Shabd path teachings of Sant Mat, Surat Shabd Yoga, or Ekankar. In some teachings, due to the multidirectional nature of the Holy Spirit, singing the name of God, who, as in human, can amplify the reception of the light and sound of the creator and open the possibility of riding the wave of light and sound back to the source, ascending to the atomic plane. When light travels and bounces off a human being, the impact of these forces upon the energetic body and how they resonate with the fundamental frequency of one's being is called the law of resonance. How these forces of light resonate with the human energy field will impact how that light code will refract through the internal DNA lens. The internal DNA lens, the state of the internal structure of light body, will dictate what experience the person will have when in exposure to the ranges of energetic frequency or spectrum of light. As a person meditates on inner stillness, intends to remove artificial machinery and clear the physical, mental, astral, causal and emotional bodies from conflict, the internal energies and chakras become more transparent and balanced. More transparency and energetic balance allows a higher capacity to resonate and reflect higher energy frequencies of the light source. Different lengths of light waves are all reflected in the same way, but not refracted in the same way. This is similar to how our personal consciousness and higher sensory perception actually work. We all share the same process in light reflection, yet we access different qualities of light waves and perceive the reality from a different clarity and perception from our personal refraction lens. As we remove and extract energies that cloud our DNA lens, we become clearer and more transparent in our consciousness light. The light particle waves at the highest frequency and shortest wavelengths bend or arc their light the most in relationship to the lens they are being refracted through at their source point. This means that the higher energy frequency light we are capable of reflecting and refracting, allows us awareness to more levels of light wave refraction made in holograms throughout spacetime. Internal light reflection and refraction are what allow us to sense multiple dimensions and planes of existence of the unseen or invisible light spectrum. Through the evolution of consciousness, we are able to sense more energy frequencies coexisting in parallel worlds or dimensions in spacetime. The human body is a holographic light projector. The human central nervous system processes electrical impulses transmitted from the DNA code, which further neurologically transmit instruction sets to the brain to perceive external images as a context for reality. A person can only experience the levels of multidimensional reality that have been programmed into the DNA code and the personal 12-tree grid, the microcosmic portion of the holographic template. This DNA program only changes when a person awakens to participate with their superconsciousness and begins to inquire on their spiritual purpose and explore their connection with all things. If one looks at holograms from different angles, they can be seen just as one sees real objects from different perspectives. Holograms contain whole views of the entire holographic image, no matter how much the hologram fragments. If a tiny fragment of the hologram exists, the whole complete picture can be rebuilt from the instruction set still held inside the tiniest quanta. Energy, radiant energy or light and higher consciousness potential are all interchangeable. Presented by Time Anti-Time. Matthew Marlin Mallory Phillips. Special thanks to Wikipedia and the Ascension Glossary. Please like, share, subscribe to Time Anti-Time and have a stellar day.